now we'll wrap up with the final technical presentation of the day by my colleague Eric Gregori from BDTI. Eric is a senior software engineer and embedded vision specialist at BDTI. BDTI is also my company. That's my day job when I'm not doing Embedded Vision Alliance stuff. And BDTI is the company that started the Embedded Vision Alliance. Pardon me, I'll get out of your way here. Eric's got a fantastic background in vision and in embedded processing, including robotics, and a variety of other applications. And he's going to talk to us about sensors. Obviously, sensors are an absolutely essential part of embedded vision systems. And as we touched on briefly earlier, your choice of sensors has enormous implications for many other aspects of your system. Mario covered the data movement aspects. It's also the question of, 2D versus 3D and so on. So Eric's going to hit some of the highlights of that and also show you a cool demo. And we've got a related cool demo running, 3D robot vision demo running on the BDTI demo table, which I invite you to come by and visit. For those of you not familiar with BDTI, we're a consulting firm specializing in embedded digital signal processing intensive applications, and I invite you to visit our website to find out more or come by our demo table.
So what I have up here is a video. Instead of trying to go back and forth with the video, I just want to explain what this is talking about. In the presentation, I'm going to cover it more, but it'll be faster if I don't try to go back and forth. What this is showing is the difference between a CCD camera and a CMOS camera, and how you actually access the camera, okay? And remember this, keep this image in your head. What's happening on the CCD side is we're transferring the charges in parallel, and then in parallel down, and then we're serially shifting them out through a converter. On the CMOS side, we're actually accessing the array of pixels individually, randomly. So you can think of the CCD as a serial device and a CMOS as a parallel device. And when I refer to this, I'm not talking about the interface to the processor. I'm talking about the interface to the actual chip, the sensor. Okay, so everything I'm going to talk about here is the sensor point of view, not the processor point of view. So let me stop that video and get on with the presentation. In there. So in this presentation, I'm going to cover sensors, the eyes of your computer vision system. Today we've talked a lot about algorithms. We've talked a lot about processors. When at the end of the day, the most important thing is your input, right? It's all about the data. Bad data in, bad data out. In your computer vision system, one of the most important decisions you're going to have to make is the type of sensors. As I'm out there talking to people on the demo floor, we talk about what kind of algorithms do you need, what kind of this, what kind of processor do you think I need. I always redirect this conversation to first, pick a camera. Pick a camera, pick an interface, then go from there. Today in this presentation, we're going to cover two-dimensional and three-dimensional cameras. It's a shortened presentation. In fact, though, there are cameras that go all the way down to 1 dimension, basically line cameras, all the way up to 4 dimensions, which is incredibly interesting. If you've got some time, do some research on the Litro camera. It's a 4-dimensional camera. It actually detects all focus ranges at once and records them. You got to look it up. It's a fascinating camera, but it just came out last year. We expect it to be very interesting in computer vision in the future, but for right now it's so new and it creates so much data, it's just not going to be applicable in the near future. So today we're going to talk about 2D and 3D cameras. This is an example of an application done using a 2D camera. In a 2D camera, what the sensor's doing is the sensor's taking a 3D point of view. The world's in 3D, unfortunately. So it's going to take a 3D point of view, and it's going to convert it to a 2D space, where the data you get out of a 2D camera is basically X and Y, and each pixel represents the luminance information in the image. That's really important, right? Because you've got a computer vision algorithm, in this case, that you want to detect a pedestrian, and you've got to do that based only on illumination information. All you know is that one pixel is darker than the next. So on the left-hand side, we have the actual raw video coming out of the camera, which in this case is black and white. The person's is darker than the background. The background's a little lighter. What you can see is we're going to pass that into the first stage of the algorithm, which is what's called a gradient map. We're going to create this gradient map. If If you look closely, the purple lines are actually arrows. And what we're doing is we're taking the gradient map, we're going from bright pixels to dark pixels. And we're looking at that gradient, and that's all that algorithm's doing, that first stage algorithm. And you'll notice that all the pixels are sort of going into the guy's body because he just happens to be wearing a black suit. We're going to use that gradient information, we're actually going to accumulate it and sum it up. That's the green and the red, the third panel in there. And based off of that information, we're going to segment and take our best guess at where the pedestrian is. Okay, so this is an application, 4 stages of the algorithm, to try to pick out a pedestrian in a scene. The question becomes, does it make sense to do this with a 2D sensor? This is an application where your first choice was, yeah, let's do it with a 2D camera. But does this make sense? Think of how much easier this would be with a 3D camera. But let's stick with 2D cameras. So how do 2D cameras work? 2D cameras come in 2 basic flavors, CCD or CMOS. A CCD camera, as I showed in that video, what a CCD camera does is it takes charges, and it stores these charges in like capacitive elements, and it shifts those capacitive elements through. I'll show you that in the next slide. A CMOS sensor is referred to as an active pixel sensor because each pixel actually has active components. Now there's some advantages and disadvantages to that. Now some overall advantages and disadvantages, it used to be that CCD sensors were more sensitive to light, so they tended to be used in more light-sensitive applications, like for instance in dark rooms and so on. That has changed. CMOS technology has come around to where a CMOS sensor, especially these newer sensors, can get light sensitivity that's as good as CCD sensors. And proof of that is actually in your iPhone. If you've got an iPhone 4S and you've read any of the articles about how great the camera is in that, that's this new type of, it's referred to as a backlit sensor. So how does the CCD work? Well, I've got this interesting demonstration here on the right-hand side. Basically, you think of a CCD, each pixel has a bucket, and this bucket's picking up charges. The buckets then move down the line, so the charges move down the line, and then they're serially shifted out. So the CCD is inherently a serial device. Some of the advantages of the CCD, though, what you can do is you can actually, if you look very closely in that image on the left, they've got a storage area, and they've got the imaging area. What they can do is they can very quickly, the storage area and the imaging area are the same thing, except for the storage area has an opaque surface over the front, so no light can get in it. So what they can do on a CCD is they can very quickly shift all the cells behind that opaque area, so you can get very high frame rates, and it eliminates things called shutter issues. If you've heard of a rolling shutter versus a global shutter, the issue becomes when you move a camera really fast, the image tends to sway like this. The CCD you can actually run in a frame rate CCD. You don't get any image movement, any image distortion when you move. And that's because of that storage area. That does require, though, that the CCD be twice as big. It's basically 2 sensors, so it's twice as big as your overall resolution needs to be. Now a CMOS sensor. A CMOS sensor, like I said earlier, the way it works is each area, it's referred to as an active pixel sensor. Each pixel is actually active. So each pixel has its own photodiode along with between 3 and 4 transistors. And each pixel is actually addressable. So the way it works is you use the row and the column to address each pixel and read the value off of each pixel. Now, if you look closely at this, you'll notice that each pixel, having its own electronics, each pixel has its own little gain. So each pixel, because there's electronics there, there's its own gain associated with it. Whereas with the CCD, there's only one amplifier in the CCD. It's all the way at the bottom there. That's another fundamental difference, and that's a really important one. With the CCD, because you only have one amplifier with one noise component, that noise affects all the pixels equally. With a CMOS sensor, each sensor has its own noise, signal-to-noise ratio. They're all slightly different. So you have to compensate for that. So most CMOS sensors, which I'm showing on the left, have an additional ISP. So you have the sensor in the center, and then you have something called an image signal processor. And a part of that job, part of the job of the image signal processor is to normalize that image. It's got programmable gains in there that automatically normalizes those pixel values. The image signal processor does a lot of other things, especially nowadays. You're going to get image signal processors to do, I double checked this, but OmniVision just released a part that does, they'll actually do image stabilization right in the camera in the image signal processor. Other companies can do compression and so on. So they're doing a lot of computer vision in the ISP. Oh, I got ample time. Okay, so before, when I started the presentation, I talked about this application where we have pedestrian detection. And the reason I picked that application was the question becomes, what is a 2D camera always the best option for a design? And in pedestrian detection, you could see those algorithms that I had to use, and even the end result was, if the guy was wearing a white suit, he'd be a lot harder to see, maybe even impossible to see. And the concept of the lights reflecting off the floor. Again, you're inferring an object based on luminosity information. That's not always the best case. So this is where the 3D sensors come in. And with the Kinect, the 3D sensor technology has really improved. And when I say improved, I mean it's actually come into the real world. 3D technology, especially stereo vision, was stuff you saw on Mars landers. With the Prime Sense, now it's in your living room with the Kinect. My kids, I stole this from my kids. They didn't recognize it was gone until yesterday. So, so yeah, I mean, this is literally a kid's toy, but it's amazing what this kid's toy can do for. And I saw it at Best Buy for $100 now, and that's that's retail. So with the 3D technology, what you get is instead of getting a light value, so an luminosity value for each pixel, what you actually get is a depth value, a distance. And that's what the image up there, it's a little dark up there, but that's what it's showing you. You can see that's what's referred to as a point cloud. And you can see the depth. I mean, it's obvious that the hand is in front, the face, and the back wall. That information is obvious just by looking at that raw data right out of the sensor. This image is what's called a depth map. And again, this came right off of the Kinect. And here, what you can see is the red. That's what's closest to the camera, and as it goes to blue, you're going farther away from the camera. Now again, just by looking at this image, you can tell right away the hand's closest to the camera. Now that's not as easy to do with the 2D sensor. So here, right away, you've got information that the closest object, further away objects, and so on. And in the demos that we have in the demo room, the robot that's running is actually using this depth map. It's looking directly at the depth map, and it's finding the closest object, and it's tracking it. So now let's think about that, because I've tried to do that robot using a 2D camera, and I can tell you the algorithms get orders of magnitude more complicated to find the closest object with a 2D camera. With this, it's literally you're just looking for a minimum. You just scan through the image and look for a minimum. That's all you got to do. Now you'll notice that there's some black. If you look behind the hand, it looks like a shadow. That is one of the limits of this particular technology. So this technology is referred to as structured light. That's the technology used in the Kinect. And one of its limitations is that it creates a shadow. It uses a projector. Structured light uses a projector to project an image, and I'm going to show you that in a second, to project a pattern. And it uses a camera that's offset to look at the pattern. Well, because the camera and the projector are offset in distance on the sensor, one's here and one's here, you can get a shadow effect, and you can actually miss data. And you're missing it there. The black in the bottom is due to distance. If an object is too close, the camera just can't calculate the distance. But the black behind the hand and on the side is caused by the body blocking the view, is the distance between the camera and the structured light source. Now, there are other versions of 3D sensors. Time of flight, for instance, corrects that problem. The time of flight sensor actually sends out a pulse of light, and looks at, actually records or measures the amount of time it takes for the light to leave the sensor and bounce back. You can actually put the light rings right around the lens so you don't have that shadowing effect problem. So the time of flight sensor actually solves the shadowing effect. The problem with time of flight, technology is relatively new. There's a couple of different methods that are used. There are a couple of different companies out there, but the technology is rather new. Stereo vision. Stereo vision is uses basically what evolution chose as the best method for seeing depth. Stereo vision uses two cameras just like you have two eyes. The idea behind stereo vision is that the distance between the two cameras creates a slightly different image, and you use triangulation. That Gary talked a lot about this. You can use triangulation to determine the distance. Problems with stereo vision, as Gary said, as you get farther away, it's a logarithmic response. It's harder to detect depth. Other issues with stereo vision, again, that Gary mentioned, you have to correct for the lenses. It's very, very hard. It's really impossible to get the two cameras perfectly set up, so you have to correct for one of them. And that takes a lot of CPU cycles. And then again, you got structured light, which is what we're going to talk about next. So the Kinect uses structured light. And here's some basic information right out of their patent. On the left-hand side, it's, again, a little hard to see because the projector is so dark. You can see the pattern that it projects. And the way the Kinect works is it uses a laser that draws about 1 amp of current. I mean, this thing gets hot. It's got a fan in it. It uses a laser through something called an atypical lens. Oh, great. Am I pronouncing that right? Astigmatic lens. Yeah, I never pronounce it wrong. It's I always pronounce it wrong. It's an astigmatic lens. And what the lens does is the lens, from a single laser source creates those dots. It projects those dots. And the way it works is the dots actually change shape based on how far away they're reflected back to the camera. So when the dot hits me here, it's a certain shape. As I get closer to the camera and the dot reflects off me, it's a different shape. They then use an IR camera, a standard VGA IR camera, to actually look at that shape and determine distance. There's actually more to it than that, but that's what they've stated in the patent. That's the only stuff that I know of that's public. Oh, and there's my astigmatic lens. Now, some of the problems with this technology, with this structured light technology, like I said, it requires a projector, so it needs its own light source. It doesn't work out in direct sunlight. You know, direct sunlight pretty much kills this thing. Even in the house, if we tried it in the main bedroom and it didn't work, or I'm sorry, the main living room and it didn't work with the light coming in through the window. Other issues, like I mentioned, because it's projecting light, it does use a lot of power. This thing draws a little over 1 amp, and there's, like I said, there's a fan in there to keep the laser cool. As a matter of fact, they actually have it's a semiconductor device that has, you apply power to it, it cools on one side and it heats on the other side. There you go. Yep, it's got one of those on the back of the laser to try to keep it cool. So that's the two disadvantages with this particular technology. You have similar disadvantages with time of flight. If you've got to work outside, the best bet is going to be stereo vision. And then let's go with the demo. So as I mentioned, I showed you before what it was like to do people detection with a 2D sensor. See if this works. Okay. So now, look how much easier it is to do people detection with a 3D sensor. Basically, all you're doing, again, as I mentioned, is looking for a minimum. It can tell where I'm at just by going through all the pixels and finding the closest pixel. And in this case, I've got more than enough CPU cycles to actually, create the skeleton, which is the next step up. So again, I mean, the point here isn't that 3D technology is the end-all. It's not the solution to everything, but it's definitely something to consider when you're making your sensor choice. Oh yeah, have you guys seen, let me go back. how many people have seen the actual output of the Kinect? So, okay, so then this might be really cool. Yeah, so up in the upper left-hand corner, you have a depth map. And then on the right-hand side, the actual Kinect has a VGA camera. So you're seeing the actual VGA camera view. That's just raw data. And then you're seeing what's called the skeleton view, which is, this is software actually from Microsoft that determines the skeleton. And they actually have games and stuff you can do. You can play a game in here as well. But again, this is something that would be incredibly hard to do in a 2D camera, which is why you don't see this a lot. It is possible, it's not impossible, but it'd be a lot harder to do. And you can see on the VGA camera how dark it is. I mean, even on my screen, it's really dark, but it doesn't matter. It's projecting an IR light source on me. You guys don't see it, I don't see it. I wonder if the camera will see it, that'll be interesting. But there you go. Now on the other hand, if it was in direct sunlight and we had windows over here, it may not work at all. Okay. So in conclusion, sensors are the eyes of an embedded system. And it's one of the most important decisions. Like I said, all too often, people sort of just assume the camera. It's a very important decision. Make your camera decision first, and then from your camera decision, decide on a processor, and then decide on algorithms. Because again, whether you go 2D or 3D is going to determine the type of algorithms you use. The other important thing about a camera that I was talking to a customer earlier about is the interface that the camera has. Mario had a great presentation on that. That's becoming harder and harder nowadays to find a camera with the right interface. Innovations in sensors is accelerating. The Sony Exmor is the backlit camera that I was telling you about. The technology is just increasing incredibly fast, being really driven by the smartphone market. And in terms of 3D technology, PrimeSense has been a big driver. We're seeing more and more 3D technology coming out. And that's it.
That's excellent, Eric. You did a fantastic job keeping everybody engaged here at the end of the day. Thank you very much.